which is actually designed to show that two-phase currents, and it contains two coils. The current, two separate electrical circuits. One coil is going through those two rings into the external circuit of the one phase, and the other coil is going through the another two rings to the another phase circuit. Two-phase alternating currents are fed into four coils. When we produce two phases current, they will, in combined action, produce the rotating magnetic field. And we can illustrate that by rotating the generator, and that will produce the rotation of the magnetic needle. So indirectly we see the rotating magnetic field effect. This is a hydraulic analogy of Tesla's rotating magnetic field and induction motor. When we produce the movement of piston in the way that two-phase current are produced by the generator, we will produce the rotating magnetic field. So you can follow the movement of electrons through the conductor by movement of air bubbles through the tubes, and by observing the rotation of the triangle, you can see the way in which the rotating magnetic field causes induction motor rotor to rotate. In 1893, Tesla showed his alternating current system, induction motors, and various machines. Here is an experiment which he performed at that exhibition. Two-phase alternating current. This is one phase current, another phase current, and here we have four coils. Those four coils produce a strong magnetic field, the rotating magnetic field. And that rotating magnetic field is going to rotate any metallic object which we place in it. Here we see an object in the shape of an egg. Induction motor doesn't require any connecting wires in the rotor, and that is that famous motor without brushes, which Tesla wanted to produce. Tesla's alternating current motor is a part of a whole system of polyphase currents. That system consists of a generator, like the one we have here. It is driven by water. Mechanical energy of water is converted into three-phase alternating currents. Those currents carry energy through the wires, first as a low voltage, then as a high voltage, with very low loss. We carry that energy through the wires. We step down high voltage into low voltage and distribute those currents to various loads, for example, electric motors. The model shown here is an example of generation, transmission, and utilization of electric energy. This is a cross-section of a modern induction motor built on the Tesla's principles. Rotating magnetic field, which is produced by the conductors which go round, is rotating, causing induced currents into the short circuit coils into the rotor. This is the rotor. And that rotor rotates under the action of rotating magnetic field in the same way as the spinning egg we have seen in the previous experiments. Millions and millions of motors of this kind are used throughout the world. You have them, many of these type of motors you will find in your own home, in washing machine, dishwashing machine, in many record players, and so on. Tesla coil producing very high frequency, high voltage, and it can operate a single terminal electric bulb. This is actually similar to Tesla single electrode bulb, which was built in a slightly different way but producing high efficiency electric light. The experiment we see now shows the effect of induction current, which can raise the piece of aluminium which you can see above the magnetic poles. Alternating current is passing through the coil and produce induced current in the aluminium piece, and that induced current are producing opposing magnetic fields, so that they try to repel each other, but then there is a gravitation, so there is a balance between gravitational force and the repelling force of the magnetic field, and it is a levitation experiment. Now this kind of experiment is used in practical single rail trains, in which case we raise the train, lower the friction, and then using a linear Tesla induction motor we can run the train along the single rail. It is very stable, as we see, because as soon as it moves from the magnetic field moves it back to the stable position of levitation. When Tesla was a student at Graz, he had a chance to see a machine similar to this one. This is a Gram machine with a commutator. That commutator produced a lot of sparks, and Tesla complained to his professor, asking him whether it would be possible to remove commutator from the machine, since every generator produces alternating current and every motor in fact operates on alternating current, but by using commutators at the transmitter or at the generator and at the receiver side. Tesla's professor said it was impossible, but later on, after many years, Tesla proved that it was possible, and he produced a brushless motor. This is a small mechanical oscillator. Tesla built several of them. One of them was used in his famous experiment when he connected it to the one part of the building and produced a vibration which shook the surrounding building, producing a small earthquake. And the same mechanical oscillator was used for another purpose, to produce a very high stability, high precision alternating current, which Tesla wanted to use for driving electric clocks. By oscillating, it produced alternating current in the coils. And vibration can be controlled by pressure, compressed air. After about 1910, Tesla worked very hard in some mechanical designs, and among them there are some speedometers, and this is one built by a firm Waltham, and it was used in Cadillac cars. This is a combination of Tesla bladeless pump and turbine. On the left is the pump, which produces high pressure, which turns turbine on the right. Piece of cable through which the first current passed from Niagara Falls power plant to Buffalo in 1895. This piece was presented to Nikola Tesla. In 1891, Nikola Tesla discovered the famous Tesla coil. That is an apparatus which converts low-frequency current into high-frequency, high-voltage current. In this machinery here, we produce a high voltage of about 200,000 volts between that and that terminal here. To show one experiment which we can perform with it, here we have a connection, a single wire connection to evacuated gas tubes here. So only one wire is connected to one side. The other terminal of the gas tube is not directly connected, and we have a wireless transmission between this terminal and that end of the tube. So the system is actually demonstrating single wire transmission of energy.
Today, the Tesla coil is used in every television and radio produced, plus many other applications. Here, Nikola Tesla is holding a bulb illuminated without wires by an electromagnetic field. This is an example of the wireless transmission of electricity.
Nikola Tesla built several huge Tesla coils. The largest one he built in Colorado Springs. That Tesla coil, as we know, contains primary and the secondary. primary of Tesla's Colorado Springs coil was 15 meters in diameter, therefore about 15 times this diameter. Secondary coil is this one with many turns, and we produce a very high voltage at the top ring, that's the last turn, and the high voltage appears between this disc and the ball, which you can see on the top. 500,000 volt is the breakdown voltage in between those two sections. In 1899 to the very beginning of 1900, Tesla spent nearly a year working on the largest laboratory he ever built, and that is Colorado Springs Laboratory. In that one, he built a huge Tesla coil with 15-meter diameter secondary coil. The top of the high voltage terminal of the transformer was connected to a high antenna. The antenna was about 60 meters high, and it was connected to the ball on the top of it.
When the Colorado Springs Tesla coil magnifying transmitter was energized, it created sparks 30 feet long. From the outside antenna, these sparks could be seen for a distance of 10 miles. From this laboratory, Tesla generated and sent out wireless waves which mediated electrical energy without wires for many miles. The old Waldorf Astoria was the residence of Nikola Tesla for many years. He lived there when he was at the height of his financial and intellectual power. Tesla organized elaborate dinners, inviting famous people who later were invited to his laboratory for spectacular electrical experiments. Nikola Tesla, financially supported by J.P. Morgan, built the Wardenclyffe Laboratory and its famous transmitting tower in Shoreham, Long Island, between 1901 and 1905. This huge landmark was 187 feet high, capped by a 68-foot copper dome which housed the magnifying transmitter. It was planned to be the first broadcast system, transmitting both signals and power without wires to any point on the globe. The huge magnifying transmitter, discharging high-frequency electricity, would turn the Earth into a gigantic dynamo which would project its electricity in unlimited amounts anywhere in the world. Tesla's concept of wireless electricity was to be used to power ocean liners, destroy warships, run industry and transportation, and send communications instantaneously all over the globe. To stimulate the public's imagination, Tesla suggested that this wireless power could even be used for interplanetary communication. If Tesla was confident to reach Mars, how much less difficult to reach Paris? Many newspapers and periodicals interviewed Tesla and described his new system for supplying wireless power to run all of the Earth's industry. This is the interior of Tesla's laboratory, showing a large number of machines supplied by the Westinghouse Company. Because of a dispute between Morgan and Tesla as to the final use of the tower, Morgan withdrew his funds. The financier's classic comment was, "If anyone can draw on the power, where do we put the meter?" The erected but incomplete tower was demolished in 1917 for wartime security reasons. The site where the Wardenclyffe Tower had stood still exists, with its 100-foot deep foundation still intact. Tesla's laboratory, designed by Stanford White in 1901, is today still in good condition and is graced with a bicentennial plaque. The Tesla Memorial Society is asking that the Wardenclyffe Tower site with the laboratory be proclaimed a national monument. We will never know what might have been if the Wardenclyffe wireless system became operational. Nikola Tesla patented the basic system of radio in 1896. His published schematic diagrams described all of the basic elements of the radio transmitter, which was later used by Marconi. In 1896, Tesla constructed this instrument to receive radio waves. He experimented with this device and transmitted radio waves from his laboratory on South Fifth Avenue to the Gerlach Hotel at 27th Street in Manhattan. The The device had a magnet which gave off intense magnetic fields up to 20,000 lines per centimeter. This radio device clearly establishes his